I don't think it's working. It says it's working, but I don't think it's working. We're just doing a few tests here. I'm just taking a look before we get into some of the highest quality probability and statistics content in the world. Because this is a channel about understanding meaning, understanding the truth, and in so doing, we have to discover different ways of finding the truth and meaning. And one of those ways is to understand truth itself. One way we understand truth is through studies, and what studies tend to use is statistics. So therefore, we are learning how to do probability and statistics in order to get closer to the truth. But first, I need to get closer to the truth of how to figure out how to get restream to work. So we're just exploring that right now. Thank you for joining me today on this journey. I'm halfway to fully caffeinated. Just bear with me, people. Okay, we've got liftoff on YouTube. Wish I could change the title. Hmm. Hmm. Okay. Let me try this. Hmm. now it works. It's a bit slow. But we got there. Okay. All right. Nice. Okay. We're in it. We're in it, people. We have achieved something today. Okay, I've gotta stop looking over there. If this is your first time tuning in, welcome. Glad you're here. This is Mind of Meaning, a channel where we pursue the truth above all things, and the way that we pursue the truth is by understanding ways of understanding the truth. Redundant, I know. And so, part of how we're doing that is a deep dive into probability and statistics. I can feel your head nodding already, and not with approval, but with sleeping, with the desire to go to sleep. And my soothing voice certainly doesn't help. But if you stick with me, you and me, together, we will achieve full truth. Yes, I said it here. Said it here first. Full truth coming your way. Okay. So, where we left off, because this isn't my first day, but it's my first day here on Kick properly. Properly. Okay. First day here on Kick. Finally figured out restream. Where we were was going through this class on at MIT. We're starting with probability, but also depending on how bored I get, we may go to other things. Last time we covered a bit of Khan Academy's stuff. I honestly got really bored and made a fool out of myself, not understanding some very basic directions on one of the little questions. Yeah, okay, stop. Just chill, okay? My caffeine had worn off, and it was just very like unexpected how they phrased it. And listen, just shut up, okay? But today we're gonna continue on our journey here. I have my handy dandy notebook here. Oops, hold on. Hold the phone. Hold the phone. Okay? If you type in chat, just know I'm gonna check it occasionally, but I really can't see it at the moment. It's just too much work for me right now to try and figure out, oh, I want to put on chat overlays. Like, just relax, okay? I really just I don't want to work on that right now. But in the future, there will be chat overlays, so I can see what you people are saying. I'm gonna check it on my other little thing over here on occasion, but really this stream is about us all getting better at understanding stats and probability. And so, as such, you all should just keep quiet, okay? And just pay attention. Pay attention. Learn something for once, okay? Just learn something. I know there's lots of other streamers out there. You know, there's hot tub streamers, there's casino streamers, and that all seems fun. But you know what? We're learning about real slots here, okay? We're learning about, like, actually how to understand the world around us, including gambling. But we don't endorse gambling necessarily. We merely understand it. As well as life, you know? Life is like a gamble. You never know how it's going to end up. And that's why we're here. That's why. That is why. Okay. So, picking up where we were leaving off. Supplemental mathematical background. I need to tell you something, people. My math is horrible. I didn't quite pass college algebra in college. I passed college, got my degree. But I didn't really, like, I got the math requirement. At the time I took college algebra, I didn't even need the requirement. I was just, I decided I was going to do really difficult science stuff, and then I realized I really can't do math that well. But I like math, in theory. I like the ideas. It's intriguing, in theory. But in practice, it's really hard. Oh. One moment. I have a whiteboard. A whiteboard. I'm getting a marker. Okay, I'm back. Now, I have this little army thing here. Not army, arm, like it's an arm. See? Honestly, a cool little gizmo I got. It was pretty awesome. And I have this set up so that I could, in theory, do have my be able to view this whiteboard from a top-down perspective. I might set that up, but we're not going to do that right now. There's a lot of features coming. Right now this is just kind of in the way, so I'm just going to scooch it over. Thank you very much. Okay, so as I was saying, I'm shit at math, but luckily, it's never too late to learn. Never too late. Never give up on yourself. I'm not giving up. I mean, I gave up already, but then I gave up on that. So now we're gonna learn the supplemental mathematical background. We're gonna get so good at math. We're gonna lay the nerds to waste with how good at math we're getting. Okay? I don't care what they've told you. I don't care what they've said. I believe in you. I trust you, and I love you. I love you very much. So let's learn math together. Hopefully, my output is coming through. My, what do they call it? I'm just checking my stuff here. Typically, around an hour and a half in, all of my equipment starts to malfunction. But hopefully that won't happen today. Okay. Oh, I gotta put this stuff back up. Look at that. It's like everyday magic. Okay. Mathematical background overview. Let's see what this gentleman has to say.
In this sequence of segments, we review some mathematical background that will be useful at various places in this course. Most of what is covered, with the exception of the last segment, is material that you may have seen before.
I've made it larger so you can take notes, because I know that's what you're doing, taking notes. So feel free to write this down if you so feel like it. And if you don't, well, be prepared to fail at life. Nobody will ever love you, and everyone will look down on you. So if you want to feel good about yourself, you will take notes and watch and not look at any other stream. But if you want to be a bad person who sucks, then leave. Go ahead. It's okay. You can leave. I won't judge you. Everyone else will, but I won't. Now, let's continue watching.
But this could still be an opportunity to refresh some of these concepts. I should say that this is intended to be just a refresher. Our coverage is not going to be complete in any sense. What we will talk about is sets, various definitions related to sets and some basic properties, including De Morgan's laws. We will talk about what a sequence is and what it means for a sequence to converge to something. We will talk about infinite series, and as an example, we will look at the geometric series. Then we will talk about some subtleties that arise when you have sums of terms that are indexed with multiple indices. And finally, probably the most sophisticated part will be a discussion of countable versus uncountable sets. Countable sets are like the integers, uncountable sets are like the real line, and they're fundamentally different. And this fundamental difference reflects itself into fundamentally different probabilistic models, models that involve discrete experiments and outcomes versus models that involve continuous outcomes.
That those things, you know, countable and uncountable sets, that those things are two different things is like, I feel like I'm not getting any real intuitive, like, understanding of what that means. Like, I sort of get it, I sort of get it. But isn't any countable thing also infinite? Whoa. Anyway, did you like that? Did you like that world? Was it good for you? We're on to the next thing. If you're new to the channel, man, I gotta work on my enunciation. My grandmother always said that. She said, you must enunciate your words. She was New England. But anyway, she always used to say I used to mumble a lot, and that was probably true. And it follows me to this day like a curse. But, where was I? We were going through these math videos. That was 0, 0. I feel like I was going to tell you a story, but I forget. Ooh, do we understand this? Do we understand these strange symbols? Well, I think we do. You and me, we're going to figure this out, okay? You probably even already know way more about this stuff than I do. And so you can help me. You can help me. So we've got set notation here. Just a little bit about my background. Before my ex so thoroughly destroyed me emotionally, I was trying to become a web developer. And I got real close too. So I have some background in JavaScript. So I know some things about some kinds of math, but just as a secret between you and me, up to that point, like I said, I failed college algebra. I was, well, it was like a D plus or something. And like I said, my math skills, my logical thinking skills were not great. So, I really had to force myself to understand programming, and I understand it probably better than your average plebe, but never could quite make it work. But I understand enough of it that it has kind of helped me in other areas in terms of thinking in that manner. I also noticed that when I was doing it, I kind of felt like a little emotionally autistic. Like I could feel myself sort of like the emotional parts of myself, the parts that connect to other humans, I could feel those parts like shutting down, and I would want to talk to people about programming, and I would watch as their eyes would glaze over as I talked to them about APIs and about connecting to databases and why it was so exciting when I finally was able to solve a problem that was causing me trouble. It was like, or when there was like a funny nerd joke that I was like, oh, there was this really funny thing that happened, and then I had to basically explain like all of programming for them to understand why it was funny. Very isolating, in fact. It's another reason why I'm not in that field. It was isolating. Okay. Has anybody showed up yet? Oh, yo, chill, relax. No, it doesn't appear to be the case. 20 whole minutes and no one has showed up. Shown up? No one is showing up. But that's okay. I enjoy my solitude. I'm alone with others, a face among the crowd. And you, dear viewer, you will be seeing this, likely, in the future. And it can be as if it were a message in a bottle just for you. Small, enclosed in glass, intimate. Okay, more math. Okay, so we've got the little sety things, right? Little squiggly lines, cute little squiggly guys, right? Finite, infinite, finite, infinite. This R here typically means the set of real numbers. That's what he's talking about here. This E is a sum. This R is the set of real numbers. This colon, I'm not sure of, but that's a cosine. I know what that means, and the cosine of x. So sum as x, some set of real numbers, cosine of x is greater than 1/2. This is the universal set we've learned. I forget what that symbol is. Is it the omega sign? I think it's the omega sign, but I can't fully remember. This is the empty set. We love the empty set. The empty set is the set of viewers that are in my channel right now. Okay, so we have the full set over here, and we have x sum set, the set subset, then x not the sum, whatever, set, da, 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 da. Okay, and he's going to explain all of this to us, and we're going to watch it and like it. Okay, so I have these stats 6 notes. I've done 6 of these little SETI things already. Mathematical foundations for stats and probs. Boink. Okay. Let's get into it.
In this segment, we will talk about sets. I'm pretty sure that most of what I will say is material that you have seen before. Nevertheless, it is useful to do a review of some of the concepts, the definitions, and also of the notation that we will be using. So what is a set? A set is just a collection of distinct elements. So we have some elements.
Did you get that? Set. A set is a collection of discrete elements. Where's my mask? I put it somewhere. Oh, you like my double E's? Save.
And we put them together, and this collection, we call it the set S. More formally, how do we specify a set? We could specify a set by listing its elements and putting them inside braces. So this is a set that consists of all elements, the letters A, B, C, D. Another set could be the set of all real numbers. Notice a distinction here. The first set is a finite set. It has a finite number of elements, whereas the second set is infinite. And in general, sets are of these two kinds. Either they're finite or they're infinite.
Did you get all that? Finite. That is some small amount. So like in JavaScript, I can show you what this would look like, because you're just dying to know. This is what it would look like. So you could do it either with an array like that. You could do 1, 2. Now you would have to use quotation marks if you were going to use a string, and we would say, buckle my shoe. That would be how we would do it in an array. We would have to declare the array. So we would say let R. R means array. Okay. Is my shit starting to... Occasionally my thing will like start flashing, and it's real super annoying. I hate it. Okay. So then if we were to do it in as an object, we would say let obj. The obj stands for object. I love treating you like you're stupid. You totally deserve it too. And then we would say 1, to BMS, buckle my shoe. That would be the object. So these are basically sets. So I taught you a little programming today. You declare your variable, and then you fill it with stuff. Good job, class. Very good job. I'm so proud of you.
A piece of notation now. We use this notation to indicate that a certain object X is an element of a set S. We read that as X belongs to S.
Oh, I thought it was a sum sign. It means belongs. Isn't that? No, the sum is like the E thing. Like it faces the other way, I think. Okay, cool. Okay, so E, we could do it maybe like that. So X, E, S. My goodness. Bunch of pervs. So the little E symbol thingy means belongs. Wouldn't it be nice to belong? So X belongs to S. So there exists some set S of which X belongs.
If X is not an element of S, then we use this notation to indicate it, and we read it as X does not belong to S. Now, one way of specifying sets is as follows. We start with a bigger set, for example, the set of real numbers, and we consider all those x's that belong to that big set that have a certain property. For example, that the cosine of this number is, let's say, bigger than 1/2. This is a way of specifying a set. We start with a big set, but we then restrict to those elements of that set that satisfy a particular property. One set of particular interest
What
is
did he
the
just
following,
say? Sorry, I was
and we read it as X does
setting up
not
my
belong
friend.
to S.
Thank you for joining me again. I just want to say how grateful I am to every one of you, big and small, short and tall. Thank you for joining me today. Welcome to Mind of Meaning. On this channel, we like to explore the truth. The truth will set you free, and we're learning stats and probability because I don't understand how studies work, and if you're like me, you're sick of being fooled. You're sick of people lying. They're filthy, disgusting lies. And so, if you're like me, unlike some other people, your goal is to better yourself. You want to be a good person, maybe even better than everybody else. And one way you're going to do that, if you're like me, is you're going to study stats and probability. Because stats and probability are the key to understanding research theoretically. Sorry, sometimes I rhyme. Okay, now, join me on this journey. If you enjoy this content, please consider supporting me at patreon.com/mindofmeaning. There, you can donate $5. That's one latte a month to the cause. We are trying to understand stats and God damn it. My camera broke. It's okay though. It just needs a little reset. I told you that would happen. Now my screen over here is going to start flickering. It's pretty annoying. Anyway, thank you for joining me, and as I was saying, please consider contributing to the cause. All right, you may notice that sometimes I rely on irony to get my point across. I mean, it may not have come through. So I'm sorry if it hasn't. Please understand, this is just entertainment. The moment caught me, and I felt like I had to express that. But we are actually on a journey to understand the truth. We want to understand the truth. The truth is how you understand reality. And reality is what we're all embedded in. We're all part of some kind of process going on. We're all possessors of minds. But if we possess our minds, then what is it that's doing the possessing? If it's not our minds, do minds possess themselves? How does that work? Wrong questions for today, because today we're doing stats and probability. I recommend you think about those things on your own. So, when I take a caffeine pill, sometimes after it starts to kick in, I get this weird smell like it's hard to describe. It's kind of like, have you ever walked into a like a gym or a dojo, like that sweat smell? It kind of reminds me of that, which, might be a little disturbing. Like what do they put into these things? Is it people? But anyway, so where were we? Belongs. X belongs to S.
Now, one way of specifying sets is as follows. We start with a bigger set, for example, the set of real numbers, and we consider all those x's that belong to that big set that have a certain property. For example, that the cosine of this number is, let's say, bigger than 1/2. This is a way of specifying a set. We start with a big set, but we then restrict to those elements of that set that satisfy a particular property. For example, the set of real numbers, and we consider all those x's that belong to that big set that have a certain property. For example, that the cosine of this number is, let's say, bigger than 1/2. This is a way of specifying a set. We start with a big set, but we then restrict to those elements of that set that satisfy a particular property. One set of particular interest.
Okay, so you could think about this like if it is true that the element of the set contains this property, then that is the element of the set that we are interested in, so we bring it back to us. That is, we are interested in the set of things that carry this condition. You could think about it as an if then statement. If then statement. Logic. We like logic. We want to understand logic logically. So that would be a way of thinking about it.
Test is the following. Sometimes, in some contexts, we want to fix a collection of all possible objects that we might ever want to consider. And that collection will be a set. We denote it usually by omega, and we call it the universal set. So having fixed a universal set, we
It was omega all along, guys. All along, it was omega. The universal set, omega.
will only consider smaller sets that lie inside that big universal set. And once we have a universal set, we can talk about the collection of all objects or elements that belong to our universal set, but do not belong to the set S. So that would be everything outside the set.
Okay. So imagine this is humanity. All of humanity. And this set is the cool kids. You and me, dear chatters, dear audience, dear people, we would be in this area. We are renegades. We are mavericks. We are on the outside of society. You see, we're a spectacle. Or are they the spectacle? Did you ever think about that? They might be the. They are the spectacle. Okay. Let's continue.
S. Everything outside the set S we denote it this way, and we call it the complement of the set S, and it is defined formally as follows. An element we denote it this way, and we call it the complement of the set S, and it is
Do you see what he did? He made it green because this is green. You see that? You see that? It's very smart. See, now you can make the connection between the green that's in the thingy, the box, and the green that's on the letter. Did you see that? It's very clever.
defined formally as follows. An element belongs to the complement of S if X is an element of our universal set, and also X does not belong to S. Notice that if we take the complement of the complement, that is anything that does not belong to the green set, we get back the red set. So what this is saying is that the complement of the complement of a set is the set itself. Another set of particular interest is the so-called
Something I notice about math is a lot of it is about saying really simple things in complicated ways. Well, because then you learn things about the thing. Like one can be denoted as 2 over 2, 3 over 3, infinity over infinity. There's an infinite ways to express the concept of 1. Except 0 over 0, that doesn't count because 0 is undefined when it's in the denominator. So saying the complement of the complement is really just saying the complement of the set of the complement. The The complement of the set is just the set itself. It's the same as saying the set. But what we've denoted there, what we've observed, is that we can take the complement of a set and find what complements it. And we get the set. Did you get all that? Did you write that down? Did you show your mom? If you haven't, do that now.
Empty set. The empty set is a set that contains no elements. In particular, if we take the complement of the universal set, well, since the universal set contains everything, there is nothing in its complement, so its complement is going to be the empty set.
Now that's an important thing to write down. Oh, darn it. The complement of the omega set is the empty set. I don't know how to do the symbol for the empty set in what is it? UTF. So we're just writing it out in words, in letters. In alpha bet. How long could I entertain myself with this stuff? So the complement of the set's complement is the set. So the complement of the omega set is the empty set. But the complement of the omega set would be the omega set. You following that logic? That's a very good chat. You're doing so well. I'm so proud of you. Thank you for putting in so much work.
Finally, one more piece of notation. Suppose that we have two sets and one set is bigger than the other. So S is the small set here and T is the bigger set. We denote this relation by writing this expression, which we read as follows: S is a subset of the set T. And what that means is that if X is an element of S, then such an X must be also an element of T. Note that when S is a subset of T, there is also the possibility piece of notation. Suppose that we have two sets and one set is bigger than the other. So S is the small set here and T
It's okay, small set. It's not the size that counts.
is the bigger set. We denote this relation by writing this expression, which we read as follows: S is a subset of the set T. And what that means is that if X is an element of S, then such an X must be also an element of T. Wow. Note that when S is a subset of T, there is also the possibility that S is equal to T. One word of caution here. The notation that we're using here is the same as what in some textbooks is written this way. That is, S is a subset of T but can also be equal to T. We do not use this notation, but that's how we understand it. That is, we allow for the possibility that a subset is equal to the larger set.
It's a very JavaScript way of writing that, not a Python way of writing it. What I want to know is, it's called Pythonic if you do something in a Python way, but shouldn't it be called JavaScriptic if you do it in a JavaScript way? These are nerd arguments.
Now, when we have two sets, we can talk about their union and their intersection. Let's say that this is set S and this is set T. The union of the two sets consists of all elements that belong to one set or the other or in both. The union is denoted this way, and the formal definition is that some
What? What? How did that even... I didn't even know you could do that. Wow. Union is denoted S U. We're gonna just do a little T. Wow. There's someone viewing me. Hello, viewer. Thank you so much for joining me. I'm grateful for your attention. If you want to write something in the chat, go ahead. Meanwhile, we're gonna keep learning stats and probability. Why? Time for my spiel. Welcome to Mind of Meaning, where we're in the pursuit of truth. We want to understand the world because we're sick of people taking advantage of us. We're sick of being fooled. So we're going to understand stats and probability so we can understand those filthy, filthy studies that those people are making. I'm just kidding. We love our scientists, and we want to understand what the heck they're saying. So we're going to understand stats and probability from the ground up. If you don't know me, I'm your host, Mind of Meaning. That is my actual name. If you believe that, that's your problem. And we are in the pursuit of truth. We are trying to understand the truth. We are endeavoring to inhabit the truth. And we're doing it by starting off today by understanding this MIT course. See, if you look, MIT OpenCourseWare, because we like free here. We like freedom. Free is in freedom. Okay? So we're understanding stats and probability. And right now we're learning about unions and intersections. It's exciting stuff. He likes it. Thank you for joining me. We're going to continue on. So this is S union T. S union T. What is the union of S and T? Let's continue.
element belongs to the union
X belong to
if and only if
S, the union.
this
If and
element
only
belongs to one of the sets or
belongs to
it
one of the
belongs to the
sets
other one of the
or
sets.
the other one of the sets.
We can also form the intersection of two sets, which we denote this way, and which stands for the collection of elements that belong to both of the sets. So formally, an element belongs to the intersection of two sets if and only if that element belongs to both of them. So X must be an element of S, and it must also be an element of T.
Now the question is, do you remember the axioms of probability? Because if you were good, then you would remember that. I don't know that I remember it, so I'm bad. The axiom number 1 was the axiom of non-negativity. Non-negativity means that probability always has to be more than 0. Greater to or equal than 0, I think, technically. It can't be negative. The other axiom was the axiom of normalization. Axiom number 2. Normalization. The axiom of normalization basically says that we can describe any probability as existing between 0 and 1. And we do that by establishing that the total set, the total population of which we study, is basically denoting 1. And any subset is therefore less than 1. That's how we can think about it. The third axiom is the one I always forget. It has something to do with how things are like not when they're not connected. Yeah, I'm gonna have to go back and review that. It's hard to get things through my thick skull. It's the greatest tragedy on earth, really. Greater than any other tragedy. But anyway, we'll review that shortly after we finish this video.
By the way, we can also define unions and intersections of more than 2 sets, even of infinitely many sets. So suppose that we have an infinite collection of sets. Let's denote them by Sn. So n ranges over, let's say, all the positive integers. So pictorially, you might think of having one set, another set, a third set, a fourth.
Okay. I was just checking to see if my stream is still functioning. Like I said, about an hour and a half in, everything starts to break down. Go ahead, give it to me. I see you're still here, all 2 of you. Welcome. Thank you for joining me. If you're enjoying this content, please feel free to support me at patreon.com/mindofmeaning. Remember that we are here to try to understand the truth, understand ways of meaning, understand significance, understand importance, understand the truth. One way that we understand the truth is through science. We love science. We revere science. But we don't fully understand science. And when I say we, I mean I, me, myself. So I'm trying to understand probability and statistics so that I can understand all those studies, those very complicated studies, and read them in all their dryness, like the desert that they are, and extract from that desert the oasis, the juicy oasis, the lush, full, fecund oasis of truth that inhabits the dryness and the, what is it called? The mirages from the heat and the emptiness of the desert of science. There's so much more going on there. And we want to understand that. So we're understanding probability from the ground up. Like I said, go support me on Patreon at patreon.com/mindofmeaning, or support me here. I'm not sure how yet. I'm just starting out. But we appreciate having you here. He appreciates you. This guy appreciates you. We're going to keep going here. So, X belongs to the intersection of the subset S and T, of the T. S of the S and T. If and only if X belongs to S and X belongs to T. This is basic logic stuff. Inclusive or, and this is and. It's basic stuff. I like these circles he just drew.
Set, and so on, and we have an infinite collection of such sets. Given this infinite collection, we can still define their union to be the set of all elements that belong to one of those sets Sn that we started with. That is, an element is going to belong to that union if and only if, and so on, and we have an infinite collection of such sets. Given this infinite collection, we can still define their union to be the set of all elements that belong to one of those sets Sn that we started with. That is, an element is going on, and we have an infinite collection of such sets. Given this infinite collection, we can still define their union to be the set of all elements that belong to one of those sets Sn that we started with. That is, an element is going to belong to that union if and only if this element belongs to some of the sets that we started with. We can also define the intersection of an infinite collection of sets. We say that an element X belongs to the intersection of all these sets if and only if X belongs to Sn for all n. So if X belongs to each one of those Sn's,
So this is basic, this feels like basic, what do they call it? Not modal logic. The, the, the one that begins with an S, I think. Do you remember? We didn't cover this on stream, but I trust that you're smarter than I am, so you should know this, and if you don't know this, then you're lesser than. You're a terrible person. But I forgive you. Okay, so I'm gonna look it up real quick. Types of logic. Yeah, you don't get to see my screen. You should have known the answer. Propositional? Not syllogism, not first order, classical, informal, fuzzy, formal. None of these. Maybe it was propositional. I don't know. What's the one that Aristotle came up with? Syllogistic? Syllogisms? But I don't think that's. Listen. I'm not the brightest bulb in the shed, okay?
then we say that X belongs to their intersection. Set operations satisfy certain basic properties.
Whoa.
One of
What
these
happened?
we already discussed.
It's a lot of
Belongs to
U's,
their
buddy.
intersection. Set operations satisfy certain basic properties. One of these we already discussed. This
Oh,
property,
hey,
for
do you remember that one? Wow. It's like seeing a celebrity.
example,
That's exactly what it's like. Fight me.
is pretty clear. The union of a set with another set is the same as the union if you consider the two sets in different orders.
Isn't that like commutative? Right? So could we call that commutative? Do you remember commutative? Oh man, it's like being young again. Commutative, if you remember, that's like 1 plus 2 equals 2 plus 1, right? So that's kind of what they're saying. The union of S and T equals the union of T and S. Those are not distinct ways of thinking about it. But he didn't say it's commutative. Why can't we call it commutative? Why can't we? Why didn't you say that? Why aren't you drawing that connection, bucko? It's fine. I'm used to being disappointed by people.
If you take the union of three sets, you can do it by forming first the union of these two sets and then the union with this one, or do it in any alternative order. Both expressions are equal. Because of this, we do not really need the parentheses, and we often write just this expression here, which is the same as this one. And the same would be true for intersections.
There's a word for that too, but I forget it.
That is, the intersection of three sets is the same no matter how you put parentheses around the different sets. Now, if you take a union of a set with the universal set, you cannot get anything bigger than the universal set, so you just get the
Doesn't this guy just sound like a math professor, though? Like the accent and everything. Is it German? I can't tell. It's very math professory. I feel like I'm in college again. Young, full of pep, so much energy, so much hope, so much life still left to live, so much trauma I haven't yet experienced, so much trauma I haven't yet processed. Those were the days.
universal set. On the other hand, if you take the intersection of a set with the universal set, what is left is just the set itself. Perhaps the more complicated properties out of this list is this one and this one.
Okay. We need to try and internalize this stuff. I've seen this stuff before, but I've seen it in the context of like algebra when I've attempted to relearn it after I got that D plus back in the day. I've like I said, I like math. It just doesn't like me. So I've tried to build a affection and a bond for math, with math, to math, and it's been difficult. Okay, it's been a rough, rocky relationship. Okay, so but we're gonna try and like really internalize this right now. So yeah, so this commutative bullshit up here, SUT equals TUS. Okay, yeah, sure, sure. Let's try to think about it. So you have a yeah, the union is like an or, right? It's like an or statement. Or you have like a circle, you have another circle, and so if you do it this way, or if you flip it around and you do it that way, it all is still just the same shit. Cool. I think that makes sense. All right. And then you got this one over here, which basically says you, you got this, this is unified with this, and then that's unified with that. Okay? You got all those things. And you can say, well, you got this unified with this thing over here, and this unified with this thing over here, and that's basically the same as if you're focusing here first. So it's kind of like salience, right? Like what's popping, like it's all there, it's all around. Okay, so like I'm gonna use my board, and if there are any math professors out there, you want to help me understand this better, I would greatly appreciate it. He would greatly appreciate it. Okay, so you got, oh, my marker is garbage. And he'll still be able to see it. You got 3 circles. Can you see that? Can you? You got 3 circles. Got my double-sided marker here. So like if we did an outline kind of like that, okay, so let me show you what I did, right? You see the darker line. I don't know if the orange is coming through, but just go with me here. And then you do something kind of like this. Oh wow. Just completely dead. Well, there goes that idea. Listen, I tried, okay? They don't pay me enough to teach you idiots this stuff. But if you want to pay me, consider going to patreon.com/mindofmeaning, where you can contribute just $5 a month. $5. That's one latte. I think I did the math once and it was like 18 cents a day. 18 cents a day. Just 18 cents a day. Contribute that to me if you love this content. If you hate this content, do the same thing. I would greatly appreciate it. Okay, so this marker is trash. Love that for me. And my black marker is really fadey. Love that for me. But basically, I mean, you get the gist. You're not an idiot. You're smart. You're beautiful. I love you. But you get it, right? So, that's basically what that means. Now this thing over here, and okay, he's about to explain it, or I forget where he's at. What time is it? It's 10:47. 10:47. I thought I started around 9. Yeah. Anyway. We're gonna keep going.
Which are sort of a distributive property of intersections and unions, and I will let you convince.
Oh, I get it. Distributed, right? So you've got S and on the outside of T union of U. So the intersection S, T, and U, T or U, is equal to S and T or S and U. Do I get this though? I need like music and sound effects for like when I'm thinking, like what Vsauce does. He's like, he starts all of his stuff off where he's like says some stupid question and then he's like, or is it? Right? And then you get like the little mystery music in the back. I got to do that. Because plagiarism is how you become creative. So, S and T union S intersection T union S intersection U it distributes the and excavates the union of those two ands. I'm trying to imagine what that would be like on a circle, on a Venn diagram. The old noggin is it's rusty. It's for sure. Maybe it was always rusty. Maybe it was always rusty. Okay, Mr. German dude, let's go.
Yourself.
If he's not German, I'm gonna feel really bad. He's just got that, you know. That's I just got gringo ears, you know.
proves that these are true. The way that you verify them is by proceeding logically. If x is an element of
Yeah.
this,
Yeah.
then x must be an element of S, and it must also be an element of either T or U. Therefore, it's going to belong either to this set, it belongs to S, and it also belongs to T, or it's going to be an element of that set. It belongs to
Okay.
S, and it belongs to U. So this argument shows that this set here is a subset of that set. Anything that belongs here belongs there. Then you need to reverse the argument to convince yourselves that anything that belongs here belongs also to the first set, and therefore the two sets are equal. Here I'm
Oh, he's
using
gonna
the following
try.
fact that if
Oh
S is
no,
a
he's not.
subset of T and T is a subset of S, this implies that the two sets are
Are
equal.
equal.
And then you can use a similar argument
I'm a genius. We said it at the same time. We're soulmates. Oh my goodness. I'm. Ah, man, I just graduated from math.
to convince yourselves about this equality as well. So this is it about basic properties of sets. We will be using some of these properties all of the time without making any special comment about them.
Wasn't that fun? Thank you for joining me. We're gonna keep going here because our project, our project is to understand the truth. I keep saying the same thing over and over again because I'm trying to come up with my elevator pitch. You know, you can't really see me with my computer here. Listen, I'm trying to get better at this streaming stuff. So I say the same thing over and over again because quite frankly, I want your money. But if you find this entertaining at all, just give me your money. It's that simple. But I'm just working on my spiel, my little talk. I do. There's a time for irony, and that time for irony is on the internet. Okay, but I am an earnest pursuer of the truth. I just think all of you people are just full of nonsense, you know, and so I feel like I'm full of nonsense. But that's okay. You know, we all have a little nonsense in us. And how do we make sense of all that nonsense? Through stats and probability, in part. That is one way of knowing. One way of knowing, of which we are earnestly and actively in pursuit of. We are searching for it, and we will find it. And when we find it, that power will be ours. And no one will be able to stand in our way. And we will be the ones in control. But until that time, we are just trying to understand what's going on in the world around us. In those science studies that exist, in the epistemology, you like that word? In the epistemic products of science, I want that power. I want that understanding. So that's why we're doing this today. It's the pursuit, in part, of power, of agency. That's what we want. And sometimes, in order to achieve agency, in order to take accountability, in order to be personally responsible for our life, we have to wade through the dullness that can sometimes be math. But there's also an exciting twinkle that glistens on every one, on every zero, every 2, 3, 4, dot, 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 n that exists. Thank you for joining me as we continue our pursuit on this path. You, me, your friends, your relatives, your mother, all of us together pursuing the truth. Thank you. We're going on to the next one. This one was about sets. How much of this did I understand? Well, not quite all of it. In fact, maybe only half of it, but that's fine. Hopefully, over time, it will sink in. But this was sets, so we're going to move on to the next of the supplemental material. This was sets. Now we're moving on to De Morgan's laws. Laws. The cause for De Morgan's laws. Laws in De Morgan's laws is Slauson. Maslaufa lossa laughing. Listen, I'm just trying to stay awake, guys. I'm out of coffee filters. I need to buy more coffee filters, so I've had to rely on pills. I've had to rely on pills, and they just don't have the same effect that they used to. They used to make me feel like a god. Now they're kind of like, don't do drugs, kids. Only you. Okay.
We will now discuss the...
What do you guys think about me reading Plato? Like on stream, not just in general? Because there's this like Neoplatonic thing. If you're unfamiliar, Neoplatonism is like a cult around Plato that occurred several centuries after Plato, and they like built this whole system of reading his dialogues to transform yourself. I think it would be fun to talk about to read it in that order on stream, but I also think that could be very fucking boring. So I might do it anyway while no one is here, just to like have the content, and then I'll just like put it all in its own little playlist on YouTube, and then people can read it at their leisure. I, for one, think I have a very soothing voice, so if I can help each one of you degenerates transform into better people, then I think that might be worth it. It's just a thought. Thank you for joining me. I'm forever in your debt, and I love you. Okay. What am I thinking? So yeah, Plato. Maybe we'll read some Plato. Maybe some Aristotle. Aristotle, as I like to say. Maybe. Maybe not. I don't know. We'll see where we get to. I've got a lot of books we could go through, maybe. I wish my markers were like darker, easier to see, maybe thicker. Maybe I'll have to set up my my other camera. But anyway, I'm just sort of thinking out loud here. I'm trying to think about what I want to do with these streams, you know? The Plato thing is an option. I'm also a musician. I can play a little guitar. I'm not great. I've been doing it for a while, but it hasn't been like a focal point of my life. I'm just kind of sloppy and, you know. But I can make a song. I can sing you a song. I'm not a piano man, but I can sing you a song. Maybe even tonight. Anyway. You think I should take another caffeine pill? I might. I'm really trying to soak all this probability stuff in. I do want to learn it. It's hard, you know? Like, this is all stuff that's very new to me. Well, you know, sort of new to me. Anyway. So who was De Morgan? You know what? This is his law. Let's figure out who Mr. De Morgan is. De Morgan. Wikipedia. Augustus de Morgan. De Morgan, de Morgan. We're going on a journey, folks. We're going on a journey. Oops. We're going on a, we're going on a journey. Look at this nerd. Look at him. Augustus. Such a pretentious name. 1806 to 1871. Alive at the same time as the great Charles Sanders Peirce, who, if you don't know, was one of the original pragmatists next to Dewey and William James, those fine, fine gentlemen. So he was alive during that era. Charles Sanders Peirce, also a logician, doing logic-y things, helping to establish computer science in his own ways of developing logic. So this guy was also a logician. He was a British mathematician and logician. He formulated De Morgan's law. Well, it's weird that it's convenient that it had that name, right? And introduced the term mathematical induction. Ooh, he developed mathematical induction. That's fancy. Making its ideas rigorous. Augustus de Morgan was born in Madurai in the Carnatic region of India in 1806. British figures. His father was Lieutenant Colonel John de Morgan. Died in 1816. Yeah, he didn't live that long, did he? Who held various appointments in the service of the East India Company. Oh, that guy. And his mother, Elizabeth Dodson, was daughter of John Dodson and granddaughter of James Dodson, who computed a table of anti-logarithms, inverse logarithms. Augustus de Morgan became blind in one eye a month or two after he was born. The family moved to England when Augustus was 7 months old, as his father and grandfather had both been born in India. De Morgan used to say that he was neither English nor Scottish nor Irish but a Briton, unattached, using the technical term applied to an undergraduate of Oxford and Cambridge, who was not a member of any one of the colleges. When De Morgan was 10 years old, his father died. Miss De Morgan, was that too soon? Mrs. De Morgan resided at various places in the southwest of England, and her son received his primary education at various schools of no great account. His mathematical talents went unnoticed until he was 14, when a family friend discovered him making an elaborate drawing of a figure from one of Euclid's works with a ruler and compasses. He received his secondary education from Mr. Parsons, a fellow Oriel College, Oxford, who appreciated classics better than mathematics. His mother was an active and ardent member of the Church of England and desired that her son should become a clergyman, but by this time De Morgan had begun to show his non-conforming disposition. He became an atheist. This is a word in our language that which I shall not confuse this subject, both on account of the dishonorable use which is frequent made of it, as an imputation thrown by one sect upon another, and of the variety of significations attached to it. I shall use the word anti-deism to signify the opinion that there does not exist a creator who made and sustains the universe. De Morgan, 1838, page 22. University education. In 1823, at the age of 16, he entered Trinity College, Cambridge, where he became under the influence of George Peacock and William Well, who became his lifelong friends. From the former he derived an interest in the renovation of algebra, and from the latter an interest in renovation of logic, the two subjects of his future life work. His college tutor was John Phillips Hogman, 1793 to 1855. At college he played the flute for recreation, and was prominent in the musical clubs. His love of knowledge for its own sake interfered with training for the great mathematical race. As a consequence, he came out fourth wrangler. This entitled him to the degree of Bachelor's of Arts, but to take the higher degree of Master of Arts and thereby become eligible for a fellowship, it was necessary to pass the theological test. To the signing of any such test, De Morgan felt a strong objection. Although he had been brought up in the Church of England, in about 1875 theological tests for academic degrees were abolished in the universities of Oxford and Cambridge. As no career was open to him at his own university, he decided to go to the bar and took up residence in London, but he much preferred teaching mathematics to reading law. About this time, the moment for founding London University, now University College London, took shape. The two ancient... God damn it. Forgive me, people. Someone rang my doorbell. I'm not sure why. I'm not sure why or from what reason. Thank you for bearing with me. We don't need to keep reading Wikipedia. Okay, we're gonna watch the video, but now we have established some background. I'm just checking to see if my stuff is still working. Seems to be. Seems to be. Seems to be. Okay. Let's continue watching.
De Morgan's laws that are some very useful relations between sets and their complements. One of De Morgan's laws takes this form. If we take the intersection of two sets and then take the complement of this intersection, what we obtain is the union of the complements of the two sets. Pictorially, here is the situation. We have our universal set. Inside that set, we have a set S, which is this one, and we have another set T, which is this one. Let us look at this side. The complement of S is this part of the diagram. The complement of T is this part of the diagram. What is left? What is left is just this region here, which is the intersection of S with T. So anything that does not belong here belongs to the intersection, and this means that the complement of the intersection is everything out there, which is this set. If you are not convinced by this pictorial proof, let us go through an argument that is a little more formal. What does it take for an element to belong to the first set? In order to belong to that set, X belongs to the complement of S intersection T. This is the same as saying that X does not belong to the intersection with S with T. What does that mean? Since it is not in the intersection, this is the same as saying that X does not belong to S or X does not belong to T. But this is the same as saying that X belongs to the complement of S or X belongs to the complement of T. And this is equivalent to saying that X belongs to the union of the complement of S with the complement of T. So this establishes this first De Morgan's law. There's another De Morgan's law which is obtained from this one by a syntactic substitution. We're going to play the following trick. Wherever we see an S, we're going to replace it by S complement, and wherever we see an S complement, we will replace it with an S. And similarly, whenever we see a T, we'll replace it by T complement, and when we see a T complement, we will replace it by T. So doing this syntactic substitution, what we obtain is S complement intersection with T complement, everything gets complemented, is the same as S union T. Now let us take complements of both sides. The complement of a complement is the set itself, so we obtain this. And now we take the complement of the other side, which is this one. And this is the second De Morgan's law. It tells us that the complement of a union is the same as the intersection of the complements. We derived it from the first De Morgan's law by a syntactic substitution. If you're not convinced, it would be useful for you to go through an argument of this kind to show that something is an element of this set if and only if it is an element of that set as well. Finally, it turns out that De Morgan's laws are valid when we take unions or intersections of more than two sets. There is a more general form, and the general form is as follows. In analogy with this one, if we have a collection of sets, Sn, perhaps an infinite collection, we take the intersection of those sets and then the complement, what that is the union of the complements. So this is analogous to this law. And this law extends to this one. If we have the union of certain sets and we take the complement of the union, what we obtain is the intersection of the complements.
Did you get all that? I'm kind of done for now. Thank you for joining me. I'm gonna go do whatever. I'll see you next time. Have a good evening. Farewell. Good morning, good day, wherever you are in the world. Make sure it's good. Love your brother, love your neighbor, love yourself. And until next time.